In this video, we'll take a look at Newman projections. So the main objective of this video is to be able to convert between Newman projections and skeletal structures and vice versa. So first, let's define a few of the terms that we'll be using throughout the video. So first of all, what is a Newman projection? Well, Newman projections are structures drawn from the perspective of looking down a certain bond. So this is different from skeletal structures because you're essentially looking at that structure from the side of bonds, so you can see all of the individual atoms, none of them are overlapping. But when you're looking down a bond in a Newman projection, there will be atoms that are involved in that bond that are overlapping. So what I mean is like here's a specific example of ethane, and what we're essentially looking at is that there's a carbon in the front that is perfectly aligned with the carbon behind it. So you can't really see it, but the way that it's drawn in the Newman projection is represented by this circle. So there's a carbon at this front endpoint, just like in our normal skeletal structures that all endpoints have a carbon. So there's one in that front, and then there's a carbon behind that carbon as well that has the other substituents. So in essence, there's a carbon in the front that's bound to HA, HB, and HC, and there's a carbon in the back that's bound to HD, HE, and HF. So in essence, just going to draw the Lewis structure or the Kekulé structure of ethane. What we're looking at in this Newman projection is we're looking down this particular bond, right? This carbon-carbon bond. So 1, 2 carbons. So there's this carbon in the front, that's carbon 1 that's bound to all these hydrogens, and then carbon 2 that's in the back. Okay, the next thing to talk about is staggered structures versus eclipsed, and these are most easily seen in the Newman projection, which is a good justification for using that in certain situations. So here are two general examples, again, of ethane, where we're looking at a staggered version, a staggered structure versus an eclipsed structure. So the staggered has all of these hydrogens such that none of them are overlapping each other, like is the case with the carbon that's in the front. That is consistent for both of these structures, that we have this one carbon in the front that is eclipsing, or it's in line with the carbon behind it, and that's the same here. But now, when we look at the differences in the structure, are there other atoms that are eclipsing or overlapping? And in the staggered version, there is not. The staggered structure has hydrogens that are as separated as possible. So this is favored by sterics because you won't have any repulsion, electron-electron repulsion, or just atomic nucleus repulsion. So this is favored versus the eclipse, where now you have, for instance, atom HA and hydrogen A and hydrogen E are now very close to each other, and there would be repulsion both from the bond and potentially from the atomic nucleus. So this is a sterically disfavored structure because, again, these hydrogens are very close to each other. And we can convert between these two by a simple rotation about that back bond. So if we look here, if we're rotating 60 degrees to the left or counterclockwise, we would put HE behind HA, which is what happens here. That would put HD behind HB, that's what happens here. And then HF goes behind HC. And I will use a molecular model to illustrate this in our next example to really tie that together. But the point is, staggered is more stable than eclipsed, and a 60-degree rotation in either direction about one of those, about that bond that you're looking down would interconvert between a staggered and eclipsed conformation. So in other words, you will go from a energy minimum at the staggered version, the staggered structure, to the energy maximum of the eclipsed by a 60-degree rotation about the carbon-carbon bond that you're looking down. Okay, so next thing to talk about is gauche versus anti. So in simple terms, gauche is simply these when you have a staggered structure. Gauche is when you have atoms close to each other, but they're not eclipsed. So for instance, this chlorine and methyl group are gauche to each other because they're close on different carbons. you would never consider something gauche that's bound to the same carbon. So like, for instance, this chlorine is not ever going to be considered gauche to HB because they're bound to the same carbon. This gauche interaction is only interesting and only defined when it is a part of two different carbons. That substituent is bound to two different carbons. So for instance, the chlorine is gauche to the methyl group, this HB is gauche to the methyl group, this bromine is gauche to HB, HA is gauche to the bromine, and so on. Those are all the potential gauche situations. I've listed several of them here just to give you a feel for it. Now, the other term that you need to know in terms of these staggered structures is anti. So anti is when you have two groups bound to different carbons that are a 180 degrees away from each other instead of this more close 60 degrees in the case of gauche interactions. So this chlorine is gauche to the is anti to the bromine because it is across from, it's 180 degrees away from the substituents from each other. HC is also anti to HB, HA is also anti to the methyl group, and vice versa. I wrote it in the direction looking at that front carbon relative to the back carbon, but you could do it the other way as well and say that the methyl group is anti to HA, and that's all totally acceptable. So the point here now is that anti-interactions are generally favored over gauche because, again, this hysterics idea, they're as far away from each other as possible, the substituents are, if it is in the anti position, because it's 180 degrees away from each other versus the gauche where it's closer, is 60 degrees away from each other. So there could be this electron-electron repulsion and other Coulombic interactions that are disfavored. So that is the main takeaway here. There are energy related to these specific interactions, and those could be provided in a specific question to rank exactly how stable a staggered conformation with a particular anti-interaction is over one that is gauche. All right, so now our point is to convert between skeletal structures and Newman. So first, let's take a look at just a standard skeletal structure, again, of ethane to just start our example here. So ethane, again, two carbons bound to three hydrogens. I've drawn it such that this HA is in the plane, meaning that this hydrogen would have no dash or wedge because it is in the plane of the paper. It's in the two-dimensional plane. Same with HD, but then HB and HE are out of the plane, represented with wedges, and HC and HF are in the plane, represented with dashes. So let's look at this with a molecular model here. So this can be very confusing to visualize, but I will do my best to represent it for you. So here, let's look at, this is carbon 1 on the left, okay? So HA is in the plane, right? So this is HA down here because it is not out or behind the plane of the paper. Now HB is this top hydrogen here marked with the little green dot, that's HB, it's coming out of the plane. HC is going in the plane, so that's HC in the back there. Then if we look at the second carbon, HD is now this one at the top on the right side, and then HE is coming out towards us, so that is this one marked with the black dot, and then HF is the one that I'm holding the molecule with, which is again in the plane. So HC and HF are on the same side of the plane, makes sense, they're both dashes. HB and HE are both on the same side of the plane coming out of the plane. Again, they're both wedges, so this makes sense. Now, one point I want to make here is usually you don't see carbon-hydrogen bonds so long. They're usually, in molecular models, they have much smaller bond length. And I have that, but I'm choosing to use this one just to show you how the Newman structures can come from the skeletal structures. Okay, so now we'll put the molecular model away for a second. So now, if you want to draw this as a Newman, you need to look down a particular bond. So I'm going to look down the 1,2 carbon bond that's labeled here. It doesn't really matter which one. On an exam or a quiz or something, they would tell you which bond they want you to look down. So there is a ubiquitous nature of the quizzes so they can grade it. So if we're looking down this 1,2 bond, the Newman projection will look like this. So we'll try to visualize this just on paper, and then I'll show you the molecular kit to explain how this comes about. So all we've done from the skeletal to the Newman is rotate this out of the plane, the entire molecule like this. So you've rotated that carbon from, you're looking at it from this side point of view like my marker, and then you turn it this way such that now you're looking down the carbon-carbon bond. So when you do that, you push HB to the right because it's out of the plane. You push HC to the left because it's in the plane. So that's what happens here. HA is now down because that is this position here. HB is to the right because it's a wedge. HC is then to the left because it's dashed. Then at the same time that you're rotating that, you're putting HD again up, and HE out of the plane again is to the right, and then HF is in the plane, so to the left. Again, HC and HF should be on the same side of the plane. They are here. HB and HE are, and HD and HA are anti, which they are in our original structure as well. So this all makes sense. So now let's go from the skeletal in showing in our molecular kit to this structure. So again, we got to get it such that it looks like this. So we have HA is down here, HD is up here. Okay, so now all we're doing is rotating this such that we are looking down this bond. We're not changing anything about the rotation of the bonds or anything like that. So now when you do that, here's HA, that's down. Here's HC, that was in the plane, which is now on the left. Here's HB, that was out of the plane, is now to the right. Here's HE and HF, again, this is out of the plane, same with HB. And HF is in the plane as a dash, is there, and HD is anti to HA. Okay, so now one more time, we'll go from the Newman to the skeletal. So simply all you're doing is rotating the molecule such that you're looking at it from the side now. And when you do this, HA is down and in the plane. HD is up and in the plane. HB is out of the plane. HE is out of the plane. And HC and HF are in the plane. So hopefully this is beginning to make sense, because this is something that you'll need to be able to do for all of organic chemistry. It's specifically quizzed in like your first semester, for instance, but you will need to be able to draw Newman projections for any given molecule to explain mechanisms beyond an organic 2 and into graduate courses or anything that you may be doing. This is a skill that is very necessary. All right, for the remainder of the video, I'm going to work through several examples converting from the skeletal structures to a Newman structure. And in these questions, we're going to be looking down an indicated bond, and that's what's going to be shown by this red arrow. That is the bond that we need to look down. And after we've drawn the Newman, we are asked to make a comment about the stability of that structure, which has to do with the gauche and anti-interactions that we initially mentioned at the beginning of this video. And yeah, so in other words, do more stable conformations exist for the molecule besides the one that they're representing and wanting you to show as a Newman? So to begin these types of questions, I think it's always useful to start with a molecular kit until you're very comfortable doing this, and then you don't need to take the time to build the molecular kit. So first, let's build this molecule. So I've already done so here. So the green atom is our chlorine. Again, I'm showing all these bond lengths to be the same. They're really not, but I'm showing that just simply to illustrate that how the Newman projection comes about, because it looks more similar if all the bonds are the same size. Okay, and then the bromine is this gray atom I have here that is down. So again, we can see that bromine and chlorine are anti to each other, even without looking into a Newman projection already. So now, how do you know where the hydrogens are located? Well, by putting the chlorine and bromine in this position, it forces the hydrogens to be in this conformation that's shown here. So I'll draw them in just to be as clear as possible. Okay, but that doesn't really matter, right? Because it is assumed that those hydrogens are there, and if they have three-dimensionality, one of them has to be out of the plane, and one of them has to be in the plane, and of course, all atoms have this three-dimensionality, right? We're trying to represent three-dimensional things on a two-dimensional piece of paper. Okay, so now if we want to take this into a Newman, we're looking down this carbon-carbon bond. So this the one that's bound to the bromine is in the front. So simply all we do is rotate this out. Let me get it lined up better. There we go. Rotate it out such that we get this type of perspective. And now this is simply the Newman. Now it's just a matter of drawing this in on our piece of paper in the way that it is shown. So we'll do that now. Again, our Newman starts with a circle. Here's our chlorine with the carbon rather with the bromine, which is down. And then the two hydrogens. Okay, and then we have a chlorine that is anti to the bromine at the other carbon. And then a hydrogen to the left and right, and there's no nothing to distinguish them here in this molecule, just because right, it's all achiral. So I could label them as HA, HB like we did with ethane, but that was simply just to show how the molecule was different. But it's unnecessary, I think, at this point. So hopefully that is making sense. So now, if you take the molecular kit away and we just look at this, again, it's a rotation in your mind. So exactly the same thing that we just did, you're effectively rotating this out like this. So now what that does is put the bromine down, exactly the same that we just saw. This hydrogen here that is out of the plane is now going to be to the right. This hydrogen here that is in the plane is now to the left. Again, I'm not distinguishing them here, so you can't really tell the difference. But if those substituents were different, then it would matter. So here, the chlorine is anti to the bromine. And then this hydrogen that's out of the plane is going to be here. Again, gauche to the other one that was out of the plane. And then the other hydrogen is in the plane. And again, these are exactly the same structures. We got them from two different ways, from the molecular model and just a simple rotation in your mind. All right, now to make a comment about the stability of this molecule. Well, the chlorine and bromine are anti to each other, which, as we mentioned at the beginning of the video, is more favored than gauche, and certainly then if the molecule was eclipsed. So this is staggered. So this is the most stable conformation for this molecule since it's staggered and it has this anti-interaction between the chlorine and the bromine. All right, here we have another example. So if we're looking at this from the skeletal, it kind of appears that this may be eclipsed because we're looking at this methyl group is in line with this methyl group instead of like the anti or trans position that it was in the previous question. So this may be a pretty unstable molecule, but we're still asked to represent the Newman projection looking down the 1-2 position. So it may have a more stable conformation, but that isn't the question here. But it's important to note because we're always interested in stability. So we're going to look at this in a molecular model, which I recommend strongly that you do initially. This is what we see here. So now here's the methyl group. Now I've shown the methyl hydrogens actually with a more accurate representation of the carbon-hydrogen bonds. They're going to be much smaller than the carbon-carbon bonds. But again, I'm still showing these carbon-hydrogen bonds because they're part of the Newman projection. So I'm still showing them as very long just so the Newman looks more consistent with how it looks on paper. So anyway, hopefully that's not confusing. But these CH3s are these CH3s. That's this CH3 is this methyl is this methyl. Okay, so you can see that they're on the same side. Then we have one hydrogen going out of the plane, one hydrogen in the plane, and then same on the other carbon. So if we want to look down this left carbon to the right carbon, so again, what we do is simply rotate this like that. And now we see that this is eclipsed. We have the methyl groups in line, the two hydrogens in line. So now I will draw this from the structure here, from the molecular model, I mean. So again, we have, start with our circle. We have a methyl group down, hydrogen to the right, hydrogen to the left. So here's a hydrogen, hydrogen, and methyl. Okay, and then it's eclipsed now. The hydrogen's in the back, so these are eclipsed here, and then the methyl group here. Okay, so now again, let's go back to just looking at our structure without the molecular model and see how we do this. So again, it's just it's a rotation 60 degrees from here to here. So what that does is put the methyl down, puts the hydrogen that's out of the plane to the right, the hydrogen that's in the plane to the left. The methyl group now is eclipsed with the other methyl group, so that goes here. This hydrogen is out of the plane, that goes to the right. This hydrogen is in the plane, that goes to the left. Right, so that gives us the exact same structure. Now, if we were asked to assess the stability of this thing, this is extremely unstable, and this is not going to be the preferred Newman projection or the preferred conformation of this molecule, right? So if we look at this, it's now possible, these carbons are all single bonds, so it can have free rotation about this bond in any direction. So if you imagine that it rotates to here, we are now anti, right? This hydrogen, this methyl group is now anti to this methyl group, and the hydrogens are just simply gauche to each other. So this would be a far more stable conformation. So this is unstable, and that's our comment. If we were asked to draw this, you would have it such that the methyl groups are anti, and that would be far more stable than this eclipsed version. All right, so here we have another question. So this is very similar to the one we just looked at. It's still a butane, but we added a alcohol. So this would be 2-butanol. And again, I recommend you starting with the molecular model until you get very comfortable with this. So this one appears to have our methyls trans to each other, which we do here in our kit. We have our CH3 are trans, and then the OH here, which is represented by this red atom with the hydrogen bound to it, is out of the plane. And then this hydrogen that's not drawn is in the plane. So let me draw that real quick. And then a hydrogen here is out of the plane and in the plane. Okay, so now let's bring our molecular model back in. And what we see, again, methyls are anti to each other. The OH here is out of the plane. This hydrogen is out of the plane. There's two hydrogens going in the plane. So now again, we're asked to look at this first carbon on the left, look down that 1, 2, or in this case 3, 4 bond. And this is what it appears to be. So now let's draw the structure from this molecular model. Okay, so start again with our Newman projection circle. We have methyl at the first carbon is down, and then this hydrogen that's green is up to the right, and this hydrogen is up and to the left. And we have a methyl here that's up anti to this methyl, and then an OH here now to the right, and then a hydrogen to the left, down and to the left. So now the question here, this is definitely the structure, but now the question is about stability, right? So we have our methyl groups anti to each other, that's good, but we do have our OH gauche to the methyl, which is less favorable than if it could be anti. So now imagine if we rotated this molecule such that the methyl was now anti to the OH. So let's ignore our structure that's here. This methyl is anti to the OH now. What has happened is our methyls are gauche to each other instead of now in this structure where the OH is gauche to the methyl. So now the question becomes which gauche interaction is more unfavorable. And typically in an undergraduate course, you wouldn't be expected to memorize that. It would be provided on the question if you were needed to assess the relative stability here. So that's how you would assess this question. They would basically tell you which gauche was higher in energy. I speculate that the methyl interaction is worse, but again, I'm not positive. I don't know how much of it. It's going to be a small difference in either case. So the bigger takeaway and the trend that you should know is that if you can have more anti-positions, then that is better. But here there is no difference. We couldn't have one with more anti than the other. There's only going to be one anti interaction and one gauche, and it's just a matter of which gauche is worse in this question. So hopefully that's pretty clear. Now, again, let's just convert this from the skeletal directly to the Newman. So again, we're rotating at 60 degrees out of the plane. So the methyl would go down. This hydrogen would go to the right. This hydrogen would go to the left. That's in the plane. This methyl is anti to the other methyl, so it's up compared to the down. And then our OH would be to the right because it's out of the plane. And as we rotate it that way to 60 degrees that way, put the OH out of the plane and to the right. And then the hydrogen that's in the plane is to the left. So again, that is the same. And then again, the relative stability depends entirely on which gauche interaction is worse, the methyl OH interaction or the methyl-methyl interaction. All right, so this is by far the hardest question, just as a fair warning. But again, it's exactly the same procedure. It's just harder because we have this bicyclic structure. So we're asked to look down this carbon-carbon bond that's where the rings are fused. So again, in this case especially, you should start with the molecular kit. So here is our structure. I'm only showing the hydrogens at the two carbons that we're interested in, the ones that we're going to look down. All the other hydrogens are there, but I just didn't want to take the time to put them all there because they're not irrelevant in drawing the structure. So now, instead of rotating the normal way, which is this way, right? We now have to rotate this way because of the way that the question is asked. We're asked to look down this bond, which is this bond here. So to do that, we have to rotate vertically. Okay, so that's exactly what we do, and we get our structure that looks like this. All right, so here is our structure. Now let's try to draw this as a Newman. And again, this is by far the most challenging question in this video. So our Newman is essentially this carbon-carbon bond, right? This front and back carbon-carbon bond. So what we have are eclipsed hydrogens, and that's easy to start with. So we have a hydrogen that's in the front and a hydrogen on the front carbon rather, and a hydrogen on the back carbon that are eclipsing each other. Then we have a CH2 group that's down and to the left on this front carbon, that's this one here, and a CH2 that's down and to the right, that's this one here, okay? And then now in the back, there is a hydrogen, there's a CH2 that again is eclipsing, that's this CH2, and a CH2 that is eclipsing, that's this one, okay? And now this is where it gets really hard to draw because we have two more hydrogens that are there are two more CH2 groups that are also eclipsing each other that are out of the way. So how I'm going to draw this, which makes it it's confusing to see, but here are those carbons. Okay, they're overlapping each other like we see here, right? They're in the same plane, but we can't see them if we do that on this piece of paper. So here now, let's label everything. Here are our two hydrogens that are out and out. The carbon that's in the front, carbon that's in the front. Here is the CH2 that's here, right? Here is the CH2 that's there, and then this is now eclipsing with this CH3, but I'm drawing it like this just so you can actually see it because they would just be in the same line otherwise. And then here is carbon 4, which again is eclipsing with carbon 1. And then here, this is now the exact same argument. 6, 7, 5, 6, 7, and 8. 7, 6, and 7 are again in line, and 5 and 8 are again eclipsing in line. And then there's carbon 1 and 2 that I didn't draw that are the last one, 9 and 10, I guess, here. So now the question with this one is this the most stable conformation? Well, it's all eclipsing, so it doesn't matter that it's a bicyclic structure. It's eclipsing, and that is definitely not favored over if you could force it into a staggered or a pseudo-staggered kind of in this case. So again, know that this is basically a cyclohexane. It's 2 cyclohexanes, but they can bend and twist into chair-like structures. So we're going to get something like that. Draw it like this, where now it's in a staggered conformation, and it kind of depends how you look at it. Here's staggered conformation with the OH, the hydrogens rather, that are gauche to each other, and then you contain the cycle. So this would be far more stable than the eclipsed version, but again, the question was asking to draw it such that it was it looked like the molecule that we were looking at. But now this is by far the more stable species. So let's draw this staggered bicyclic structure as a Newman here. So again, we're looking down this carbon-carbon bond. So that puts our hydrogen up here on the front carbon, and then there's a CH2 left and down, and a CH2 left and down, or right and down rather. And then there's a hydrogen here that's gauche now to this one in the staggered position, and then there's a CH2 up and to the left, and then a CH2 down. Okay, so now we have to connect this carbon to this carbon, and that's where these two come in. So there's 1 and then 2, and then we connect. Right, so there should be 1, and then the carbon in the back is 2, 3, 4, 5, 6. That's our 6-membered ring. And then if we look at this other one over here, the other ring, again, we have the same kind of thing where we have 2 carbons that are linking this. So carbon 1, 2, 3, 4, 5, and then 6 is in the back. So this is by far more stable because it's a staggered conformation of the bicyclo structure instead of a eclipsed like we had initially. So that is all I have for this video. I hope this really helps in understanding Newman projections. Again, like I mentioned earlier in the video, this is extremely challenging, so be patient with yourself and practice, 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 and you'll be able to do it like a pro. All right, that is all I have for this video. I hope you enjoyed it. If you did, please leave a like and subscribe to the channel for more content like this. If you have any questions or any suggestions, please feel free to leave them in the comment section below, and I'll get to it as soon as possible. But with that, I hope you all have a great day, and I'll see you in the next video.